All right. So let's get started. Solid state physics, lecture 3, and we are going to look at thermodynamic properties of solids. The start of this will be from a historical perspective, but this historical perspective is extremely useful because you will see how ideas were introduced gradually into solid-state physics from the quantum theory. I told you that by my definition, solid-state physics is a study of solids armed with quantum theory. At the same pace as quantum theory itself was being developed, at about the same pace, those concepts were being transposed into solid-state physics. And it's also great for learning because this gradual introduction of quantum mechanics is nicer than starting with a true picture. However, these two models that we're going to look at today, Einstein's model of solid, Einstein got his hands dirty with everything, and Debye, they are capturing some aspects of real solids, but not all of them. And so they are approximate models. Actually, Debye's model is pretty useful, has some limitations. And Einstein's model does not explain things too well, but it was a great step in the right direction. So keep in mind that later in the course we will learn more detailed models that take into account the crystal structure of solids, and those will be done a little bit later. So today what we're going to look at is calculations of heat capacity and how people were confused by the mismatch between some of the naive or simple expectations from classical physics and what was actually measured in experiment. And so heat capacity is how much internal energy increases when you increase temperature, right? So heat capacity is dE by dt. And this is what we know, or what we knew from classical physics. So classical statistical theory of thermodynamics can give you the result that heat capacity is just a constant, and it's proportional to 3n k. K is Boltzmann K in this course, right? K is most of the time will be Boltzmann K. And 3n is the number of atoms in a solid. So basically each degree of freedom contributes k Boltzmann by 2 to heat capacity. For each atom you have 6 degrees of freedom, 3 translational, 3 rotational, and this is how you get to this number 3nk. And historically it's known as the law of Dulong and Petit. These were the guys that postulated this law, and must say it works pretty well for many, many solids around room temperature. So it is a good guess for the heat capacity of a solid is to just take this number and you'll be okay. You will not be quite okay for some solids. For example, for diamond, this is off, and we will learn why this is the case. For diamond, this law of Dulong-Petit fails already at room temperature, and it really fails at low temperature. So people observed, as the cryogenic technology was improving further and further, people were observing that as you cool things down by a little bit or by a lot, heat capacity drops. So solids are unable to hold as much heat at low temperatures as they do at high temperatures. And this is completely unaccounted for by classical theory. Classical theory just gives you this law of Dulong-Petit, that heat capacity is flat and has no temperature dependence. Right? So this was a pretty strong motivation for people to, keep keep coming up with better theories for this and keep looking for other solutions. And also, this was more than 100 years ago, and people it was really big. It was a big thing to measuring heat capacity of things. So, you have a thermos, an isolated can, you know how much heat you put in. You can measure temperature, or you can do it the other way around. So this was a big thing, and mapping out heat capacities it turns out from something so detached from what we think about now, about solid state physics, things like crystal structures and making devices and creating new materials. You can learn a lot from heat capacity. So this fairly boring thermodynamic property is very revealing. And so what people typically observed in experiments is something like this. Heat capacity would stay pretty close to this 3n times k number. So with volume, it would, of course, go up. That's what n is from. And then it would start to fall down. And then around some threshold temperature, which here is called theta d, we will see later what that is, it crashes down. And then it reaches actually 0 at absolute 0, right? So at 0 Kelvin, it reaches 0. And so at 0 temperature, solids are absolutely incapable of holding heat. Now, the origin of this graph, I think this is actually a fit from the Debye's model. So we will see it towards the end of the class today, what Debye model is. But for now, let's treat it as just a cartoon. This is what, in a cartoon way, was observed. With experiments, we have always some error bars. So what was observed is that it was slowly falling down and then just crashing down below some temperature and then actually approaching 0 as people were able to cool things down lower and lower. They were seeing that heat capacity drops farther and farther. So to be more precise, this is the dependence that people found in many of the real materials. That at low temperature, down here, heat capacity had this functional form. So heat capacity was proportional to T cubed, and that's in all solids. And then in some solids, especially in conductors, if you do very careful measurements, you could resolve this additional linear contribution. Yeah? So if you can fit really, really well your data points for heat capacity versus temperature, people concluded that there could also be a linear contribution. Now, we will not discuss this linear contribution today. Our goal for today would be to get through all the models and get to the understanding of where this T cubed might be coming from. Right? The heat capacity dropping as a T cubed was a huge clue that classical physics is insufficient and we need to look for something quantum mechanical. And just the fact that it falls down. Okay. And so Einstein proposed the first model that had some success. Actually was a huge advance compared to the classical theory. And basically what he said is, look, remember the harmonic oscillators? So what do atoms do in a solid? Well, they are stuck in position by forces that hold them together, by interatomic forces, described in chapter 5 of our textbook. They're stuck together, but they can vibrate. They can vibrate in 3 dimensions. So let's treat them as a bunch of oscillators. And in this case, he meant really uncoupled little oscillators. So one atom sitting at a crystal site just vibrates independently from other atoms. And let's calculate heat capacity for this kind of system, assuming that this is a quantum harmonic oscillator we are talking about. Okay? So applying what we reviewed last week about the energy levels of a quantum harmonic oscillator, and so on. So each atom vibrates independently. That's a very important assumption of the Einstein model. And then, if you remember, for the energy levels of a simple harmonic oscillator, we had this formula and so we have one of these at each side, or maybe in a three-dimensional form. So this is a one-dimensional form, but then we have the same oscillator in 3 dimensions. And now the question is, well, what is this omega? And Einstein said, well, it's something. And so he called it Einstein's omega. No, probably he didn't, but somebody after him did. So this is some unknown parameter that maybe we can adjust it later on to make it fit our experimental data. Maybe we can deduce it from the materials properties of different materials in an independent way. But for now, this is just a parameter that is presumably dependent on material that we're studying. Okay, so now let's look at, for now, just one-dimensional oscillators in this lecture, and then we will probably just multiply that by 3 to get to the 3 dimensions. And let's see how this description is different from the simple classical description with having K Boltzmann half for the heat capacity of each atom. So the main difference is, of course, coming from the fact that this is now Bose-Einstein statistics that we're dealing with here. And to figure out the average energy per oscillator, we need to use that notion, right? So now, whereas in the classical physics we had to deal with the equipartition theorem, this is something that tells you that per degree of freedom you have K Boltzmann divided by T in heat capacity, but doesn't matter what that degree of freedom is. Here, we're going to calculate heat capacity the following way. We're going to find the E total and we're going to do that by finding, this is 1A, finding E average per oscillator and then multiplying it by n, or 3n. That's going to be our finding of E total. And then we are going to take a derivative of E total with temperature. Okay? This is going to be our methodology for this hour. Okay, so this is the formula that I already introduced to you in the previous slide. So each oscillator has a ladder of these energy levels. Now, what does Bose-Einstein statistics teach us, just conceptually, before we go through the formulas? It teaches us that at a given temperature, there will be a number of bosons occupying this harmonic potential. This number is not necessarily fixed. So there could be several vibration particles living in this harmonic oscillator. But the occupancy of them will change with temperature. So in general, at higher and higher temperatures, higher and higher levels in this simple harmonic oscillator will be occupied. Right? And so those will be described by Bose-Einstein statistics. What would be the average occupations of them for a given energy at a given temperature, and so on. So this is what's going to be happening. As we increase the temperature, higher and higher levels get occupied, and we will have larger and larger energy per oscillator, average energy, and then the total energy, we just assume them to be independent oscillators, so the total energy will also grow with the average energy per one oscillator. And as that has a temperature dependence, we will be able to take that derivative and find the heat capacity. Okay, and you can already see that one thing that this theory should be able to predict is that heat capacity goes to zero, because eventually all these vibrations are going to start freezing out, and it will be difficult to excite to the next level if there is not enough temperature left. Okay. Now, to do this calculation, we are going to use this notion of partition function, right? The partition function is this function z here, and what is written here is the single particle partition function. This is a pretty universal formula. If you have a set of states where you go through some index r, for now we don't know which what that index enumerates, but we sum through all energies E of r, and then the partition function for that thermodynamic system will be given by a bunch of exponents. So I know some of you know this, and some of you don't know what partition functions are. So I encourage you to look on CourseWeb for a little tutorial about that. But what we need for this lecture, I'm going to introduce it here. Okay. So this partition functions are particularly useful for dealing with systems which can have many possible states. Okay, so for example, a gas of atoms, and the position of each atom is a state, there could be an enormous number of states. In that situation, what you can use partition function for is to calculate, for example, the average energy, which is exactly what we need to find. So this is very useful. How does it come about? If you have many states that a system can take, then statistical mechanics teaches you that the probability to occupy one of these states is proportional to the exponent in minus beta, the energy of that state. Right? So this is maybe a little bit intuitive from Boltzmann distribution, for example. Right? So the higher the energy, the lower the probability of that state. So in large systems, this is the case. So then the sum of all probabilities will give you the partition function. Right? And if you want to calculate the energy, say the average energy, for example, you may want to do something like this. Sum of energy times the probability, and then partition function will come out as a normalization factor here. So then you can use some math to show that if you want to calculate the energy, the average energy, and you already know the partition function, for example, here is already a calculated partition function for the harmonic oscillator, okay? Nice surprise. Then it is an equation like this: minus 1 over z dz d beta. Let me write it again. Minus 1 over z dz d beta. And you can, again, I'm not going to derive it here in this class, but you can see where this can be coming from. Here in z, energy is in the exponent. Right? So you want to take the logarithm of both sides and then since average energy has energy times the exponent, this hints at derivative being taken, right? So if you take a derivative of the exponent, you'll get energy in front of the exponent. So this is very, very coarsely how this derivation goes. The point is, there is this partition function, and it's a resource for getting exactly what we want, the average energy. And so we will proceed for the Einstein's model by calculating the partition function. Following the definition of partition function, we need to take exponents of the energies of a harmonic oscillator. So we plug this into the definition of the partition function, and then we use a formula like this, and that gives us the average energy right away. Okay, just a reminder, in all these slides, beta is 1 divided by kT, Boltzmann K. Right? So beta is inverse temperature here. Okay. So the way it goes is we plug in the energy of a harmonic oscillator into this exponent. Now it has two terms. One depends on n, and the other one is this constant that is independent of n. So this constant, we can take it out of the sum. And then we have this simple series of exponents with different n here. And so there is a well-known result for what that sum gives you. It gives you 1 divided by 1 minus the exponent of the first term in this series. And so this is coincidentally the Bose distribution. Okay. So now we have a partition function. We lost the ability to flip slides. Oh, it's here now. It's playing with me. Okay, and now we're going to use this next formula to find the average energy per oscillator, per one oscillator, given the known partition function that we just calculated with a little bit of math. All we need to do is take a derivative of that function with respect to beta. And once again, I'll write it a few times. Beta is 1 over kt. So this is the function from the last slide. And when we take a derivative of it, we take a derivative with respect to beta. That's pretty easy. Take it in parts. And you get this term. This is now the average energy that is stored in one harmonic oscillator at a given temperature. The temperature is hiding in this beta. So this is now temperature-dependent energy, and you can see that this is not this will not give you a constant when you take a derivative of this. Right? So this is not going to be a classical situation where heat capacity is a constant. Well, luckily, all we need to do is now differentiate this with respect to temperature. And this is a bit more messy because temperature is in a denominator of the exponent here. So now we go from beta to temperature, and therefore we have to differentiate with something which is a denominator of the exponent. We do a derivative at a constant volume. That's because the volume of a solid is approximately constant. The solids change volume a little bit with temperature, but we can still take a derivative with constant volume. And so after some algebra which involves taking a derivative of this expression with respect to temperature, we arrive to this formula for heat capacity, which is the Einstein's model result. Any questions about this? I think this math is also in the textbook, and it will be in the slides that I post online. So what we did is we made an assumption that a solid can be made up of simple harmonic oscillators. We've calculated the average energy per oscillator, and we took a derivative of that to find the heat capacity, in this case, of a single harmonic oscillator. And now we remember that we don't have a single harmonic oscillator. We have 3n of them because we have 3 atoms and they live in 3 dimensions. And so the final result is the same formula, but it's just multiplied by 3n. Each oscillator has a heat capacity given by this exponential equation, and then we have 3n of them. Okay, so let's see how Einstein model does with respect to real observations. We can start analyzing this by looking at the limiting cases of this formula. And the 2 obvious limiting cases are 0 temperature and very large temperature. Right? Now let's see what the formula gives us in these 2 cases. So let's first look at high temperature. So when temperature is high, that means beta is small, right? Goes to 0. So beta is very small. Okay, so looking at this formula, we're going to have a very small beta here. So we can expand this term in beta. And so, exponent of what is it? I call it x can be expanded as 1 plus x plus and so on. And so this is what is done here. We've replaced exponential term with 1 plus beta h bar omega Einstein. The one upstairs just becomes 1, and this still has beta. Okay, however, these ones cancel, and we have beta squared in the denominator and beta squared upstairs. So these 2 cancel, and we arrive to the classical limit. Right? So we recover the law of Dulong-Petit when we assume that the temperature is large enough. So that is great. That means Einstein's theory matches up with the with the classical theory at high temperatures. So that's pretty good. The problem with Einstein's theory is actually at low temperatures. It predicts something that the classical theory that experiments don't observe. So if we look at this formula now, let me erase some of my markings here. We look at this formula again, formula for the heat capacity. We can see that when temperature goes to 0, beta is very large, and we are going to have this proportional to an exponent minus beta. Right? So it will going to be 3nk beta h bar omega e squared. We can forget about this 1 because the exponential term will be huge. And so we'll have single exponential here and the squared exponential in the denominator. So this is going to be proportional to exponent to the minus beta h bar omega e. So indeed, heat capacity is going to go to 0 when beta goes up and T goes down. Heat capacity will be 0 when beta is infinity. However, it's not going to be T cubed. that was observed experimentally is going to be exponential. So the discrepancy between real solids and Einstein's theory is at low temperature. So you see Einstein introduced this model, say, okay, let's treat them as quantum harmonic oscillators. He got some success. Starting from room temperature, he could show that heat capacity should vanish. That's already pretty good. However, failed to recover this T-cubed dependence. So it's partially successful. Now, I'm going to have to go here to flip the slide. It was still pretty successful, right? But actually, if your data is not very good, and this is something that all of you, and especially those that go into science, any kind of science, I want you to remember, if your data is not terribly good, I mean, all data is great, right? We're talking error bars. You know, how large are the error bars in this direction, also in this direction? How well can you know the temperature, for example? And if your data is not particularly good, it is actually not so easy to tell the difference between exponential decay and the power law decay. So between T cubed and exponent, sometimes it's hard to tell. However, you can tell. So this is the best fit that Einstein himself did, in fact, based on somebody's experimental data. In 1907, he made this fit. And even in that early paper from 1907, you can kind of tell that his points, his fit is not reproducing perfectly the experimental data. But, you know, back then, who knows what, what was measured. There are obviously some points that are very odd. Here, the Einstein's fit predicts that it should drop a little bit faster. This experiment seems to suggest that it should stick around 3 kBt a little bit longer. So intermediate, maybe it's a bad data point, or maybe the theory also fails in that regime. We don't know. But overall, he adjusted his H omega, his Einstein frequency for this material. This is diamond. And he was able to fit it pretty well. I think he was probably happy with himself, and we should also be. By the way, this is diamond, and this is what I mentioned to you, that already at high temperature, heat capacity is not perfectly 3 kb. This is normalized by the number of atoms. And this is because you actually have to go to even higher temperatures to make it approach that. You had a question?
I wasn't sure what the units were on the x-axis, but I see that.
Right. So these are both normalized. This is the theories doing some fit. Even Einstein did these things. But actually, this is quite useful, right? To normalize your x's, and then you can see all materials can be on the same plot together. All right. So I want to show you also data that is more recent. In this case, this is from 1958. And here people were, gotten much better data than Einstein had. So this is still diamond, but this is just a low temperature regime. Again, this is a strange parameter on the axis, T cubed. So to find the real temperature, you have to take a cubic root of this axis. But this is the heat capacity. And in these coordinates, a cubic dependence would look like a straight line. That's the whole point of plotting it like this. And then you can see with very high accuracy, the lowest data point is that they measured down to is 12 Kelvin. That's already very cold. And down to 12 Kelvin, you can see that it follows a T cube dependence. And on this, with this quality of data on this plot, we can really tell whether this is exponential or a power law. Right? Exponential would still look exponential on this plot, and this becomes a straight line. So it's not exponential. And this turns out to be a big deal, that it's not exponential. So this is not some minute thing, some small discrepancy. We cannot say, okay, Einstein got it, and there are some little tweaks we have to make to his theory. We have to make another huge leap forward to have a more effective theory that describes just this one parameter heat capacity. And we have to embrace quantum theory on another level. And that's what we're going to do now. Who did this was Debye. And Debye also borrowed from quantum theory, but like I said, on a higher level and in a very creative way. So the principal difference between Einstein's model and Debye's model is stated here. Atoms are bound in a solid by interatomic forces. They are not actually pinned to some imaginary sites and they vibrate around them. When one atom vibrates, the next atom should feel that. They're all coupled together. And so what Debye, without considering the gory details of these couplings and whether they can be anisotropic and so on, Debye just said, well, if these are coupled springs, then why don't we work with these waves that are created once atoms are coupled? And now we call these waves phonons. Phonons are, this is not perfectly applicable to just the simplest Debye model, but I'm going to use this term phonons anyways. I'm an experimentalist. I'm allowed to do such things, to not be perfectly precise in these things, as long as we get the concept. So these vibrations that propagate through solids, or sometimes they're called phonons, or just vibrating modes of a system of many, many coupled oscillators. Let's quantize those, right? So rather than quantizing the vibrations of one atom at a time and then just multiplying it by 3n, let's quantize the waves that travel through the crystal. Right? This is Debye's model. And we're going to get a slightly different result based on that. Now, this was a great idea. After that idea came, actually Debye didn't have to do that much. Well, still quite a bit, but he didn't have to do that much because there was already Planck's description of light at that time. It already existed. And so you probably know from your modern physics or other classes that what Planck did, he did a great thing. He explained these experimental curves for intensity of radiation that comes by itself out of solids, and how that there is a peak in that radiation and how that peak shifts with temperature to higher and higher frequencies. And he was, in his department, in these waves, he was also very successful in explaining why the experiment looks like this, and the classical theory predicts some divergence where at higher and higher temperatures you just have more and more energy coming out of a solid, and there is no limit to it. And the explanation was that light is emitted by quantized waves, by particles of photons, and then the thermodynamics that comes with that, Debye just took that and transposed it onto phonons, onto vibrations, onto waves that live in solids. There are some differences that we have to take into account. There are some differences between light and vibrations in a solid. And this is one of these differences, and it's from the fact that you can have transverse and longitudinal vibrating modes in a solid. So basically, what Debye said is that these vibrations, these are atoms moving closer and farther apart, and these as well. We describe them by, just waves. So there must be solutions to some wave equation. For example, something like this with some amplitude, and they travel. And we know how to quantize these based on Planck's description. So they're waves described by wave vector k. And so in the case of light, there are two possibilities. Light can oscillate this way, and light can also oscillate this way, right? So the electromagnetic wave travels along the pointing vector, and then electric field can oscillate with one polarization, and electric field can oscillate with another polarization. And those are two degrees of freedom that you have. Here you can also have these transverse modes. So let's say if this vibration travels this way and atoms displace orthogonal to the propagation direction, and then there is one more direction in which this can happen, right? So two orthogonal directions. But a wave can also be breathing along its propagation. So a wave of matter can also do this other thing, and that's a longitudinal wave. So there are three possibilities, not two as for light. So that's one difference, and this becomes important because we want to know heat capacity, and we need to count energy per degree of freedom ultimately, right? So this is going to be important. How many to count. And this is another important thing, and this is a concept that will follow us throughout the course. And it's the fact that all materials have boundaries. We don't have infinite materials, and we have finite sizes, limited by the number of atoms ultimately. So we have n atoms per solid. And that means that this wave, this phonon or this vibration of atoms is different from light in another important way. Because light, once it's emitted, or if it travels from minus infinity from a distant star, it can just go forever. It is in free space, and it's not constrained by anything. But this wave will hit the boundary of the crystal. And so there will be some boundary conditions necessary that will restrict the space of available solutions that we have. Okay? So like with Einstein's model, let's just constrain ourselves to a one-dimensional chain of atoms and think about what happens with waves in one dimension. Basically, one way to write boundary conditions is this. So if we have n atoms in a chain, let's make a boundary condition in which these atoms actually form a circle. So the first atom and the nth atom are the same. Now, this is one particular way to define boundary conditions. We could define other boundary conditions, something like hard wall or other boundary conditions. So which kind of boundary conditions you impose does not play a very big role. So this is as good as anything. So now we did something very abstract, right? Because now, first I was talking about a solid, a chunk of something. Now I said, okay, let's just focus on one dimension. And in that one dimension, let's put atoms on a circle and connect the first atom and the last atom to be the same atom. So this is pretty far from what we actually have in reality, but this works just as good as anything else. So under these abstract boundary conditions, we have the following constraint. So the first atom is like the last atom, or the nth atom is like capital N plus nth atom. This is a more general form. So if we skip by capital N atoms, where capital N is the total number of atoms, we should have the same phase of the wave. We should be in the same position. And what that means is simply that this must always be true. And it turns out that, okay, this is a exponent of a complex number. So this is like a sum of a sine and a cosine functions, and those functions are periodic with a period of 2 pi. Right? And that means that this expression in the exponent, without I, k and a should be equal to 2 pi n. For this to be true, and this means that, remarkably, k can have only these values, no other values. Okay? Here we replaced n times a with L, the length of the chain. So A is the distance between two atoms, n is the number of atoms, so n times A is equal to L. Okay, so K is restricted. So unlike photons, which can have any K in space, in free space, any K is allowed. You can increase K by as much as you want or as little as you want. In a crystal, due to these boundary conditions, we end up with a set of K vectors, and nothing in between is allowed. Where this, an easy way for you to understand why this must be the case is because we are talking about vibrating modes of a system of coupled masses, right? And if you work back to your mechanics, there cannot be an infinite number of modes for such a system. And the number of modes must be limited by the number of masses that vibrate. Right? So a chain of coupled masses would vibrate and would have the number of modes that is equal to the number of masses. And this is exactly the case here. So if we take the available range of K, the full range of this K is 2 pi divided by, so in the K has the units of 1 over distance, so it's 2 pi divided by A is the range of K, and then we take spacing between modes, which is 2 pi divided by NA. That's the spacing between modes. So this is a series of K's that runs from 2 pi A, from minus pi A to plus pi A. K belongs to this. And inside that, we have K's with these spacings. This just comes all from this formula. This is pretty easy. But if we take the range of K divided by the spacing, we get N. So basically, there are only N modes in a crystal. It's limited by the number of atoms that you have. Right? So it must be limited, and this is why, this is the physical motivation for introducing these boundary conditions. So this is just a way of restricting the number of modes that are allowed. Okay. So what we're going to do now is, again, calculate the total energy of all these particles. And we could do it with using the partition function, or we could do it this way, where we already know that these are bosons, and that the occupancy of each mode is given by the Bose factor. And this is what Planck did. So this part Debye just copied after saying that he wants to quantize vibrating modes in a crystal. He copied this from Planck. So what Planck did, in his turn, he said, okay, these are the energies of harmonic oscillators. Let's take the Bose-Einstein statistics and plug it instead of this n. This will give us the average or the expectation value of energy at a given temperature. So rather than plugging in the partition function, you can do it this way, the way Planck did it. So Planck said, okay, take the formula for levels of a harmonic oscillator, but the n in that formula is a Bose factor. And get the expectation value for the energy. And then we need to find the total energy of all the waves. And for that, we take the energy of one wave and multiply by the expectation value. Oh, sorry. We take the energy of one wave. We take the expectation value for one wave and sum it over all the waves. So now the difference with Planck's approach, once again, is that the k's here are a limited set. So they're not all k's are allowed. So we have to plug in k's from this series. Now, a proper description is always to use the sum. However, in a solid, we have an Avogadro number of atoms. We have a huge number of atoms. And therefore, it is conventional to go from sum to an integral. And this is an easy way to do it. So rather than summing by k, we integrate by k. And now we do it in the range of allowed k, from minus pi over a to plus pi over a. And this is how many states we have per decay. Okay? So we assume that there are so many states that even in one decay, in small infinitesimal small change of k, we have some states. And so this is how many we have. And then we integrate this function, this e. You can check that this is a correct formula by doing what is done in this blue box. So if we just take this integral of dk without any function, we're going to get n. So the total number of modes is still n. Okay? So if we take this integral from minus pi a to pi a, we're going to have this expression, the prefactor na divided by 2 pi, and k will change from pi a to minus pi a. So this is just 2 pi over a, and this will cancel with this a over 2 pi, and so the total number of modes is n. Okay, so this is the same doing this sum and doing this integral. And so when we go from sum to an integral, we have total energy written down like this. What people also often do is, rather than summing by k, when things don't depend on the direction in space, when it's an isotropic system, it's also convenient to integrate by omega. And so you can do a transition from integral by k to an integral by omega. And when you go from one to the other, you may have to add this function g of omega here. So once again, this integral counts the number of states, right? And so here we did it explicitly, so we know that if we take this integral, we will get n modes. And so what this g omega does, you can already deduce, it tells you how many modes you have per d omega. For each omega, how many modes. And so that when you do this integral, you will have the right number n. So this g of omega is a very common function that we will encounter many, many times in this course, and it is called density of states, right? It makes sense. It's how many states in this interval of d omega at a given omega. So it's like density, but for states. And if states are equally distributed in k, they may not be equally distributed in omega. Right? For example, if you go from 1D to 3D, there could be many different k's, but the same omega. You have to integrate over a sphere, and so on. Okay. So here they give you what the density of states is. And if we make another assumption, which I think Debye did in his very simple calculation, we can also say that omega and k have a linear dependence on each other. So I think this is what this theory assumes. It doesn't have to be like this, but in this calculation, we're going to assume that there is this sound speed, right? Speed of sound, and all phonons, all vibrations in this crystal propagate with the same speed, and then k is just proportional to omega. This doesn't have to be like this. In fact, it's not like this in general. But for this simple calculation, we're going to assume this. And this gives us already pretty close. Okay. So in terms of the integral, this is what we need to calculate. This is now a three-dimensional form. So we were working with 1D. Now this is a three-dimensional form. And in 3 dimensions, we have this integral over k in 3 dimensions. We can still reduce it to integral by dk by doing this transformation. And so you can see that this is already becoming a messier and messier integral by the time we get here. And so that's why it's easy to switch to the frequency integral. So by the end of the day, total energy is given by this integral. Now, what is also another assumption that is on this slide, so in addition to the assumption that density of states is a constant and proportionality between k and omega is just linear, you also put this cutoff here. So it turns out if you don't do that, the integral diverges. So Debye had to introduce this cutoff in an ad hoc way. We have to have some maximum frequency to which we take this integral. We cannot integrate through all the modes. It does not give the right result. So this is a funny aspect of his theory, but we will see that it is well justified and has a good physical interpretation when you look at experimental curves. Okay, the rest of this is algebra, going from 1 dimension to 3 dimensions, changing from integral d3k to dk, changing to omega, and arriving to some integral. Okay, the rest is math. We're going to define something that is called the Debye frequency to take into account this prefactor here. Turns out it will also be connected to the cutoff. in the end. But in terms of the Debye frequency, some characteristic frequency, we can rewrite this integral in this form. And this is an integral that you can just take by looking it up in a table. Now remember, we had the two cases we had to account for. High temperature case and low temperature case. So at high temperature, we need to merge with the classical theory. And at low temperature, we need to recover the T-cubed dependence. So this is a little bit of a tedious part, going through all this algebra. I think it's very useful to look through this also on your own or study it in a textbook. But let's not lose track of why we're doing this. And this is to reproduce the experimental observed heat capacity. So now let's go to low temperatures. At low temperatures, this Bose-Einstein term will give a very, very small contribution at higher frequencies. And so at low temperatures, we don't actually need to put this cutoff here. This exponent here will take care of that. The occupation of higher energies will be so low that we can just go ahead and replace that cutoff with infinity, and then it becomes easy to take this integral. Well, I'm not going to do it now, but it turns out that this integral like this just gives you a number, which we can just plug in. So it turns out this is the integral. As long as we're allowed to integrate to infinity, this is all that we need to worry about. And after we're done with this integral of this form, we've done the substitution, then we have the expression for the total energy of the system. And this means we are one step away from heat capacity. So heat capacity is just derivative with respect to temperature. And so we have the total energy. We take a derivative and we get this expression. Okay. This slide has a bit less stuff, so let me discuss what this means using this slide. Okay, so first of all, what did we actually do? Well, we assumed that all atoms in a solid are coupled, which is a really good assumption. It is like that. And then, following Debye, we decided to quantize the vibrations of the entire solid the same way that Planck did with photons. Right? And so then we realized that what Planck did is to get the total energy, he just plugged in the Bose factor into the energies of the harmonic oscillator. That's very simply what he did. And that allowed us to calculate the total energy and then calculate the heat capacity. We also had to include the boundary conditions. Right? And so we have this formula now. Now, this formula is not so surprising because if you remember Planck's theory, then energy was proportional to T to the power of 4, also for photons, right? I think it's called Stefan Boltzmann law. So this was the case for photons. It is also the case for us. The derivative of this with respect to temperature gives us a T-cubed dependence, right? So I could have also told you, without going through all this math, I could have just told you, well, we use Planck's approach and energy is proportional to T to the 4th, so then heat capacity should be proportional to T cubed. And we're going to have some pretty good agreement at low temperature. Right? And so this is what Debye's approach gives us good agreement at very low temperatures. So heat capacity of a solid due to that is, this heat is stored in vibrations of the crystal, and it's given by this formula, and there is this Debye temperature in it, which is related to Debye frequency And this is, is similar to to Einstein frequency. It is a parameter that's material specific. It is not, however, just a frequency that defines one harmonic oscillator, right? This is a frequency that emerges from in the formula, right? So it's given by this expression. It has the speed of sound. It has the volume of a solid, the density of particles in it. So this is a very different from Einstein frequency and where that comes from. And this is some kind of collective, but it is similar in the sense that it is also a characteristic frequency that gives us some scale, and it's dependent on each material. Okay. Now that was low temperature, and we are very happy that we recovered this T cube. This is not just matching slightly better the experimental data. It required this insight that we need to quantize the waves of vibration to get this. Turns out we can also do this. We can also match Debye's theory to the law of Dulong-Petit, to a classical theory. Well, we have to go, for all things classical, we have to go to high temperature. And so we go to very small beta, once again, like we did with Einstein's theory. And in that case, the Bose factor in our equation transforms, like I already told you. We replace the exponent with 1 plus beta, h bar omega, and instead of an exponential, we have this prefactor, this Boltzmann prefactor. And so now, this equation must always be true, regardless of whether omega is proportional to k or not. And we plug in this into our expression for energy. So we integrate from 0 to omega max. Now we cannot avoid this omega max. If we don't do it, then it will diverge. And we have integral of d omega times the density of states times the energy. This is the energy. And so instead of the Bose factor, we plug in this simplified expression. H omega cancels, and what we recover in the end is that the total energy is equal to N times K times T. Now, this implies that we plugged in the correct omega max, right? So this answer will obviously be dependent on how far we integrate. And so we need to use the right omega max. And omega max, we can get it from this expression. Turns out that this comes from the same fact as the boundary conditions, that the number of modes in a solid is limited. It must be n, or 3n, depending on how you count, for whether you're in 1 dimension still or in 3 dimensions. This makes this offset be not random, not some ad hoc thing that Debye just added, but it makes it physically justified. Okay. So this is a comparison of two models that we looked at today. Now on the same graph, there are two solid traces here and the data from experiment. And one of the solid traces is difficult to see because it overlaps pretty well with the data points, right? You can see that there are two solid traces in this region. And so one is from Debye, one is from Einstein. Debye theory seems to work better, quite a bit better. They both go to this thermodynamic limit of 3 nkt, or if you replace nkt with r, the r constant, then it goes to 3r. However, at low temperature, Debye model wins over Einstein. Einstein predicts a much more rapid decay, and Debye theory accurately reproduces the t to the cube dependence. However, this is not the whole story, otherwise this would be the end of the course. These are some of the things that were too simple, done too crudely by Debye. Okay. This cutoff, so the guy encounters an integral that diverges, and he said, okay, let's put some cutoff. We can interpret this cutoff in a physical way, but it doesn't come naturally out of the math, right? So it's just something where we just don't integrate further. The underlying Bose of Einstein physics would allow you to keep going in your integration. You could, in principle, have higher modes, but we just say, okay, no more modes. We have to count to n modes, and that's it. So this is a little ad hoc, but it is very successful. This cutoff is a very common practice in even modern solid-state physics, I must tell you. We have assumed this very simple dispersion relation, this is called. So the connection between frequency, hence energy, and momentum is linear, and there is a single sound velocity. This is an oversimplification. It is not true for all vibrations. It is true for some. As it says here, it is known that at high enough frequency, the law of omega equal to Vk no longer holds. There should also be, this law can also not work when you just get to the level where the wavelength is similar to the atom size. This simply cannot work. So this is a simplification. Turns out that, I guess for the most part, this just introduces a numerical difference to the Debye theory. Doesn't work as well at intermediate temperatures. Cannot tell from this graph, but I guess people who really studied Debye theory versus heat capacity of different materials concluded that it doesn't really work too well in this region. Okay. And this is very important. Conducting materials have this form, and this is actually still always dominated by T cube unless you go to really, really low temperatures where gamma starts to win. So for all practical purposes, Debye theory accounts for the most important contribution to heat capacity. But the fact that there is this contribution is extremely important. And it's, again, like with the lecture of today, we could account for most of what's happening at room temperature. There are some small deviations, but if we dig into why there are these little deviations, we drag this entire apparatus of quantum mechanics into solid-state physics. It's the same with this little term. So next time on Thursday, we will understand why this is important and how this comes from heat carried by the subsystem of electrons that are living inside the solid. Okay? So they also contribute, and the fact that it's this linear dependence turns out to be very important and very revealing in terms of new physics. And we stop here and continue on Thursday.